That works for me.
Okay. Do you want to go first or second?
I can go first. I have the problems up. How did everyone find the test? Easy, hard, okay?
I thought it was a bit harder than last one.
A bit harder.
Yeah.
What
For me,
about other folks?
my major problems were question 11 and 12.
Okay.
Yeah, same here. Same here.
Well, we can go through all of them just to make sure, because I think no one got all of them right, so it might be useful to just go through all the problems. And then I know for my problems, at least on combinatorics, there were a couple of basically like new techniques or new tricks on top of what we learned that I kind of like put together in the problems. So it might be helpful to go through all of them. So let me start screen sharing here. Now that I have it up. Oh, I think Matthew, I need your help on screen sharing again. Thank you. I think that worked.
Please, when will we get the results back?
I think they should be already graded. If you haven't gotten the email, then either Matthew can look into it while I'm going over the questions, or I can look into it afterwards. I think we probably just have to press send to send the results over. So I'll get them to you during this class or right after. But if you have your answers with you, you can also follow along, and then you can also kind of self-check. So I'll go through all the combinatorics ones first, which was every other problem. But while we're on the topic of combinatorics, and so Matthew and I don't have to switch back and forth, we can just do all combinatorics first. So the first combinatorics question on the test was, find the maximum number of points of intersection between 12 lines, given that 4 of them are all parallel to each other. So do you all remember the question we did in class about the maximum number of points of intersection between, say, like n number of lines?
Yes, please, there was a formula.
Okay, yeah, so suppose we ignored the part that any of them are parallel. What's the maximum number of points of intersection between?
That's 66.
That would be n choose 2, or in this case, 12 choose 2.
Right, yeah, that's correct. So maximum, max number of intersection for 12 lines, not parallel, is 12 choose 2, which was 12 times 11 over 2, which is 66. And just to refresh, the reason that this is the case is for every point of intersection, it's a set of 2 lines that are intersecting to cause that point, or to come up with that, create that point of intersection. And so if we want the maximum number of points of 12 lines, the max is going to come when all of them intersect each other one once. And so if we want to find how many ways there are for 12 lines to intersect each other, that's going to be 11. 12 choose 2, so 12 times 11 over 2. So now we have to take into account the fact that 4 of them are parallel to each other. And so in class, we did a question that was like, what if 2 of them are parallel to each other? And when 2 of them were parallel to each other, we decided to subtract 1, because that meant that for one pair of parallel lines, that was one intersection point that we don't have, because those don't intersect. So in this question, it says 4 of them are parallel to each other, right? So we could maybe do an example here. So say we had 5 lines and 4 of them were parallel to each other. We would get 4 points of intersection. If we had 6 lines, so let's say n equals 5, the maximum number of intersections for 5 lines is 5 choose 2, which is 10. But if 4 of them are parallel, then we only have 4. What if n is 6? Then the maximum is 6 choose 2, which is 15. But let me just try to draw a 6th one. The total number of intersections is going to be 9. So I saw that on the test, a lot of folks subtracted 4 from 66. And we see using these small examples that if you subtract 4, you're not going to get the right answer. And so what we actually need to do here is find between 4 lines, how many points of intersection could there be, and then subtract that out. So what's the maximum number of intersections for 4 lines?
So that would be 4 choose 2, right?
Yeah.
So that would be 6.
Yep. So we actually need to subtract out all of these potential intersections that are not happening when 4 lines are parallel to each other. So we actually have to subtract out 6. And in these small cases, we see that's also true. So if we subtract 6 from 10, we get 4. We subtract 6 from 15, we get 9. And for the 12 lines case, we have to subtract 6 from 66 to get 60. So I think a lot of people were very close on the test, but we, instead of just subtracting 4, for the number of lines, we actually had to take into account 4 choose 2. Any questions on this? All right, I'm going to move on to the next question then. So this one, it was a path counting question. So basically it says Amanda is walking a path from 0, 0 to 8, 8. And when she's standing at a point m, n, she can either take a step by kind of increasing the x coordinate, which is going to the right, or increasing the y coordinate, just going up by 1. And then the question says, how many paths can Amanda take that go through the point 3, 2? So to make this a little bit easier, let me spend a little bit of time trying to draw out a grid. Sorry, it's not perfectly square. All right. So let's say that this is 0, 0. This is 3, 2. And if I did this right, this is 8, 8. All right. So basically, Amanda can travel in this, when it says the second statement. She can either increase the x coordinate or y coordinate by 1. That's basically saying she could travel at any point this way or this way. And then the question says, how many paths can Amanda take that go through 3, 2? So for example, this would not be a path we want to count, although it is a path from 0, 0 to 8, 8. But we want to count all the paths that kind of go through 3, 2. So in class, we learned about how to count the number of paths from, say, one point to another in a grid. And so we could break this down. Because we know that Amanda has to go through the point 3, 2, we can first count how many paths there are from 0, 0 to 3, 2, and then count how many paths there are from 3, 2 to 8, 8. And then to combine it together, this is where we use the rule of multiplication. So whatever paths we have from here, so say I pick one path here, I can combine that with any number of paths from here. For example, that, or this, etc. And so to get the total number, we need to multiply all the possibilities here with all the possibilities here. So can anyone volunteer? How do we count the paths from 0, 0 to 3, 2, and from 3, 2 to 8, 8?
I think that it would, from the number of paths from 0 to 3, 2 would be 5 choose 3.
And can you give a quick explanation of why that is?
Because I don't really remember.
Okay, that's okay.
Could I help out?
Yeah.
Because there are 5 total moves. There'll be 3 to the right and 2 upward. So that's how you get the 5 factorial. And you can choose to do choose 2 or choose 3 because you are moving 3 right and 2 upward.
Mm-hmm. So the number of paths from 0, 0 to 3, 2, like you said, you have to go right 3 and up 2. And so basically we want to count how many orderings are there of this. And so the way that we could count this is we say, okay, well, we have 5 sort of moves that Amanda has to make, and she needs to pick 3 of them to be right, or 2 of them to be up. And so to count this, we can do 5 choose 3 or 5 choose 2, which is 5 times 4 over 2. So that's 10. And then similar question, how do we count the number of paths from 3, 2 to 8, 8? Someone else want to volunteer?
Well, it would be, I think it would be 11 choose 8 because of the fact that we're moving 5 in the y direction and 6 in the direction of x, and when you sum that together, it's 11. And when you take one of the coordinates for that we're given is 8, so 11 choose 8.
So super close. You're right, we have to go right 5 and up 6. So we basically want to see how many orderings are there of 5 R's and 6 ups, or 6 U's, for example. So to do this, instead of choosing 8, we actually want to choose 5 for R's, or we can choose 6 for U's. So it's actually going to be 11 choose 5 or 11 choose 6. And if you expand this out, it's basically 11 times 10 times 9 times 8 times 7 over 5 times 4 times 3 times 2 times 1. So this is we can say this is how I would do it. Cancel it out. And then this is 11 times 42, which is 462. So then the total number of paths equals, I'm just going to write it out so you can all follow along. Number of paths from 0, 0 to 3, 3, 3, 2 times number of paths 3, 2 to 8, 8. And then we calculated what these are. This is 10 times 462, which is 4620. Any questions on this one? Awesome. I think a lot of people actually got this one right, or were really close on this one. So good job. All right, we'll move on to question 3. So this is a slightly different counting problem that I put on the test. So this question says, Andy has 10 red M&Ms and 12 green M&Ms. How many ways can he distribute them to 3 kids such that each kid has at least 2 red M&Ms and at least 2 green M&Ms? So the reason I put this on the test was it kind of builds on to some of the concepts that we were learning in class. So let me pose maybe a simpler question. Suppose Andy has 10 red M&Ms and he just wants to distribute them to 3 kids. And so there's no requirement that each kid has at least 2 red M&Ms or anything like that. Can anyone remind us how to do something like that? Or anyone have any ideas?
You have to use the star and bars.
Right, awesome. So the first thing to recognize with this problem is basically like, how can we model this in a way that kind of reduces the problem to something we already know how to solve. And so in this case, it's kind of a stars and bars problem because we have 3 kids and we want to divide some whole number of things to them. And it's so that each kid ends up with a integral or non-negative integral number of things. And so we can reduce this subproblem, say Andy has 10. Three kids, no restrictions. We can reduce this into a stars and bars problem. So suppose we just consider this easier case. How do we solve this with stars and bars?
Well, we know that in at least there will be at least 10. One of the values when we're solving for stars and bars, if we write it as a plus b plus c equals 10, one of the values is going to be 10, and we'll have 2 bars. So we add 2 to our value 10, which makes it 12. And so we then have 12 choose 2 because we have 2 bars, and that will give us the number of ways.
Right, so here's an example. We have 10 stars and 2 bars. And so this might represent a solution like A equals 3, B equals 5, C equals 2. And to count the total number of solutions, like Salorm said, it's going to be 12, choose 2. And this is 66. All right, so we solved that sort of subproblem. now let's consider the slightly harder case, which is, let's say Andy has 10 red M&Ms. And there's 3 kids. And then each kid gets at least 2 red M&Ms. So any ideas on how we can take this into account?
What we did last time when we encountered something like this is that we added 2 to each variable, since that's the restriction. So no matter what the value is, even if it's 0, we'll always have them already having 2 or into themselves. So we'd say a plus 2 into brackets plus b plus 2 into brackets plus c plus 2 into brackets, and then we subtract the 2, and we subtract all the 2's from 10, which will leave us with a plus b plus c equals 2. Sorry, equals 4.
Yeah, that's right. So there's a couple ways you can think about it. Here we're transforming the problem by just kind of saying each kid, in this case, each kid gets a plus 2, b plus 2, c plus 2 M&Ms. And to make it more clear, we could say, like we could call this a prime, b prime, c prime. And basically, if a is still the number of M&Ms that the kid gets, b second kid, and c the third kid, then we could say a equals a prime plus 2, b equals b prime plus 2, and c equals c prime plus 2. And then we kind of transformed it to a problem that we already know how to solve, which is how many non-negative integer solutions, a prime, b prime, c prime, are there to a prime plus b prime plus c prime equals 4. Another maybe like intuitive way to think about this is if I have 10 M&Ms and I know each kid has to have at least 2, I can first sort of take out the 6 M&Ms for them, give each kid 2 of them, and then I basically have 4 M&Ms left to divide among them. And so each time we get a prime plus b prime plus c prime equals 2. And then again, when we do stars and bars here, in this case, we're going to have 4 stars and 2 bars. And so the number of solutions is 6 choose 2, which is 15. All right, so now we have some solved a subproblem, which is about the 10 red M&Ms. Now let's do the green M&Ms. So Andy has 12 green M&Ms. How many ways can he distribute them to his 3 kids such that each kid has at least 2 green M&Ms? Any ideas on that one?
Yeah, so we take the same procedure as the one we just did, making it a prime, a is equal to a prime plus 2, b is equal to b prime plus 2, c is equal to c prime plus 2. Then we have the a prime plus 2 plus b prime plus 2 plus c prime plus 2 equals 12. Then we just solve it.
Okay, so what do we get in that case?
Solving everything, you'd get 28.
Say that again?
At the end, the very end, you get 28.
You get, sorry, maybe I'm just misheard you.
28.
Oh, 28, sorry. Okay, cool. So to express that in terms of something, choose something, basically we have 6 stars and 2 bars. And so you get 28 if you do 8 choose 2, right? And that's 28. Cool. So now we have solved these kind of 2 subproblems here. So let's go back to the original problem. Andy has 10 red M&Ms, 12 green M&Ms. How many ways can he distribute the M&Ms to the kids where there's green ones and red ones? And so we have answers for the red ones and answers for the green ones. So how do we combine these together?
You multiply.
Yep. So basically here, we want to multiply them together because these are two sort of distinct events. So Andy can choose how to divide things with the red M&Ms, and then separately he can choose how to divide things with the green M&Ms, and then we want to count every combination of those. So we want to multiply these together, and so the total is 15 times 28. And I believe this is 420. Any questions? All right, let's move on to question 4. This one is a little bit different, but it's similar to what we were doing above, right? Above we were solving, finding the number of ordered triples where a plus b plus c equals an integer. Here it says find the number of ordered triples a, b, c where a, b, and c are non-negative integers that satisfy a plus b plus c is less than or equal to 20. So any ideas on how to do this?
We know that for any combination of 3 numbers, that there would be six order triplets for those. So then we can just find out how many combinations are there that satisfy a plus b plus c is less than or equal to 20, and then multiply that by 6.
Okay, so I guess ordering that would work if we actually had 6 orderings for everything, but I just want to caution that if you're looking at sort of maybe like partitions of 20, like say let's say 5, 5, 10, that actually maps to only 3 solutions, which is 5, 5, 10, 5, 10, 5, 10, 5, 5. Whereas if you have distinct numbers such as 4, 6, 10, then this will map to 6 solutions, which is 4, 6, 10, 4, 10, 6, 6, 4, 10, 6, 10, 4, 10, 4, 6, 10, 6, 4. So multiplying by 6 may not get you the right answer unless you're doing it very carefully, depending on how many are distinct.
Oh, I thought I don't know why I assumed this, but I thought A, B, and C had to be consecutive.
Oh, okay, gotcha. No, there's no requirement that it's consecutive. So I'll give a hint for this one. So basically, we already know how to solve something like, suppose this were not less than or equal to, but we want to find number of ordered triples A, B, C, where they're and integers such that a plus b plus c equals 20. So this was something we were just looking at in the previous problem, right? This is stars and bars. And basically we would have 2 bars and 20 stars, right? So how do we solve the case where it's, instead of it being equal to 20, it's less than or equal to 20? So we can maybe transform this problem by thinking about it as, so I have 20 stars and I want to put them in 3 different buckets by separating them by 2 bars. But since a plus b plus c could be less than 20 as well, we could pretend there's sort of a 4th bucket that we want to put something in. And anything that's in that 4th bucket doesn't go to A, B, or C. So, for example, let's use the balls and urns analogy. So say, 3 urns, and I'll label these A, B, and C, and I have, 20 balls that I need to put in the urns. So that will tell me how many solutions there are to A plus B plus C equals 20. But in this case, the total number of balls and urns A, B, and C could be less than 20. So let's suppose we have this, extra urn, I'll call it D. So now if I have 20 balls and I'm distributing them between A, B, C, and D, that will map to a solution of A plus B plus C is less than or equal to 20, depending on what D is. So for example, if we put no balls in D and we distribute all the balls just in A, B, or C, then that's going to give us solutions of A plus B plus C equals 20. If we put 1 ball in D, that's going to give us solutions to A plus B plus C equals 19, and so on. So we could transform this problem into how many solutions are there to A plus B plus C plus D equals 20, where A, B, C, and D are non-negative integers. And then this is a problem we know how to solve. So can anyone remind us how to solve this?
Using the stars and bars process, you'd make it 22 choose 2, I think.
So it's
Sorry,
close.
23. 23.
Yeah, so
choose
it's
3.
close. We have 20 stars and 3 bars. So the total number of solutions is going to be 20 plus 3, choose 3, which is 23, choose 3, which is 23 times 22 times 21 over 3 times 2. And if you do this math, I think it's going to be 1771. Does anyone have any questions about this one? Does everyone see how or why we transform this less than or A plus B plus C is less than or equal to 20 question into an A plus B plus C plus D equals 20 question? All right, I'll take silence as no question. All right. So this one's a different question. Find the number of subsets of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 that are subsets of neither these smaller subsets 1, 2, 3, 4, 5, 6, nor 5, 6, 7, 8, 9, 10. So any ideas on how to do this one? I know a couple folks got this right on the test. How did you all do it?
You could
So
find
basically,
the total subsets for the original set, and then find the subsets of the sets we're not allowed to use and subtract.
Okay.
so basically you take 2 to the power of 10 to find the number of subsets in the first one, and then basically subtract 2 to the power of 6 and subtract another 2 to the power of 6 from it. I mean, yeah. And then you have to correct for overcounting.
So how do you correct for overcounting?
you subtract another one.
Sorry, what do you subtract?
2 to the power of 2 to correct for overcounting.
So why is it 2 to the power of 2? Can you explain? That's right, by the way.
Because 5 and 6 are repeated.
Yeah, so here we're counting all subsets of 5 and 6 twice, both in when we're counting this and when we're counting this. So we also want to count number of subsets of 5, 6, and this is 2 power of 2. All right, so let's put this together. So we've counted number of subsets of 1 through 10, that's 2 to the 10th. A number of subsets of 1 through 6, which is 2 to the 6th. Number of subsets of 5, 6, 7, all the way to 10 is also 2 to the 6th. And then, as was pointed out, number of subsets of 5, 6, which is kind of the intersection of these two sets. So this is 1, 2, 5, 6, intersect. That's the symbol for set intersection. Is 2 squared. So if you remember a couple classes ago, we learned about the principle of inclusion and exclusion. So if we want to count the total number of subsets of, or this one, we're going to take the number of subsets of this first set plus the number of subsets of the second set minus the number of subsets that are subsets of both. So that's going to be 2 to the 6th plus 2 to the 6th minus 2 squared. And then we're going to use complementary counting to count the number of subsets of this larger set 1 through 10 that are not subsets of either of these. So the total number we are looking for is 2 to the 10 minus 2 to the 6 plus 2 to the 6 minus 2 squared. And if we expand this out, this is 1024 minus, and then 2 to the 6th is, I think this is like 256 minus 4. Because this is just 2 to the 7. Sorry, 128. 128 minus 4 is 2, this is 2 to 7. And then this gives you 1024 minus 124, which is 900. Any questions before I move on to the last combinatorics question?
No, please.
Awesome. So this one was problem number 12, and I actually had 2 parts to it. So we'll go through each one. So this first one asks to find basically find the value of the sum, which is 99 choose 0 plus 99 choose 1 plus 99 choose 2 all the way to 99 choose 99. And then I said we could, instead of, I don't want you to multiply it all out, basically you can give me the prime factorization of x. And as an aside, sometimes you'll see this in summation notation. So you could see this expressed as something like k equals 0 to 99 of 99 choose k. So we learned something similar in class on Tuesday. Does anyone remember what we could use to solve this? So let's suppose we have a set S equals, let's just say the first 99 integers. And say we want to count the number of subsets of S. If we want to count the number of subsets of S, one way we could count it is by just counting kind of directly. We know that we just solved a problem, problem number 5 above. That was counting numbers of subsets. So how many subsets are there of S?
2 to the 99th power.
Right. So if we count directly, the number of subsets of S is just 2 to the 99th. Another way we could count the number of subsets of S is we could basically break this up into casework. So if we first count number of subsets of S, say of size 0, plus number of subsets of size 1, plus number of subsets size 99. That will give us the total number of subsets. So we're just going to count, how many subsets have no elements in it, how many subsets have 1, how many subsets have 2 elements, how many subsets have 3 elements, how many subsets have 4 elements, all the way up to how many subsets have 99 elements. Does everyone see why if we sum all these up, that gives us the total number of subsets?
Yeah.
Yeah. And so how many subsets are there of size, say, K? If K is between 0 and 99, are there of S, which has 1 through 99?
I think it'd be 99 choose K.
Yeah. So basically, if we want to get a subset of size K, basically we want to say how many ways are there for me to choose K elements from S. And so this is actually going to be 99 choose 0 plus 99 choose 1 plus 99 choose 2 plus 99 choose 3, all the way up to 99 choose 99. So then what we see is that X equal, which is 99 choose 0 plus 99 choose 1 plus 99 choose 2, all the way up to 99 choose 99, is actually 2 to the 99. And this actually generalizes. So as a review of what we talked about in class, if 99 were some other number, right? Say we just had a set 1, 2, 3 to n, then we can kind of apply the same principle. Say we want to count the total number of subsets of this set. If we count it by first counting how many subsets there are of each size, then we get n choose 0 plus n choose 1 plus n choose 2, all the way up to n choose n. And if we count it just directly by saying for each element, it could be in the subset or not in the subset, then we get 2 to the power of n. And so generally this is sort of a true identity, a true statement for n greater than or equal to 0. I'm not going to use n here, k 0 to. So as an aside, this is something that could be useful in the future. But we sort of derived this from scratch using counting. Any questions before I move on to part 2 of the problem?
No, please.
All right. So part 2, it's a little bit more complicated. So this one's same kind of question. Basically, how do we express this sum? And again, I just asked for the prime factorization so you all don't have to expand it. And if we want to write this again in summation notation, we could do something like k equals 1 to 100 of k times 100 choose k. And so to solve this problem, we might try to use a little bit of algebra because it looks very similar to a sum we know how to calculate, right? So we already know how to calculate something like this. We might want to see if we can transform this sum into something that looks more like what we're looking at above. So looks like my screen mirroring froze. Just give it a sec to catch up. Can everyone see the problem? Okay, everyone can see that?
No, it went off.
Yeah, no, I can't see anything. I think it just showed, it just, yeah, look, now I can see it.
Okay, cool. I think I was just lagging a bit. All right, so basically I was just saying we already solved above how to basically sum, I'll just write it down here, something that looks like this. And we notice that this looks very similar, but it's not exactly the same. So we might try to do some algebra to see if we could transform it into something that's closer to something we already know how to sum. So we could play around with something. Say we have something like, I'll just use an example, like maybe 7 times 100, choose 7. This is one of the terms in this series. So if we expand this out, we actually get 7 times 100 factorial over 100 minus 7 factorial times 7 factorial, right? And this is going to be 7 times 100 factorial over 93 factorial times 7 factorial. And we could cancel out the 7s and get 100 factorial over 93 factorial times 6 factorial. Does everyone see any questions so far?
No, please.
All right, so when we see 93 factorial and 6 factorial on the bottom, that kind of looks like we could do something like 99 choose 6 because 93 plus 6 is 99. So we could rewrite this as 100 times 99 factorial over 93 factorial 6 factorial to make basically this quantity look like 99 choose 6. So this equals 100 times 99 choose 6. And more generally, if we have n, I won't use n, k times 100 choose k, where, you know, k is greater than or equal to 0, less than or equal to, say k is less than or equal to 100, greater than or equal to 1, because that's what we have in the sum. We could do the same thing where it's k times 100 factorial over 100 minus k factorial, and kind of want to cancel out the k's. So we can do k times 100 factorial over 100 minus k factorial, k times k minus 1 factorial, cancel out the k's, and this gives us 100 factorial over 100 minus k factorial, k minus 1 factorial. And again, we could kind of see the same thing when we have these 2 factorials at the bottom, where one is, you know, something minus k factorial and then k minus 1 factorial. We might want to change it back into a combination again. And so here we could rearrange this as basically, instead of writing it as 100 minus k, we could write it as 99 minus k minus 1 to make it more obvious what we're doing here. And we could write this top one as 100 times 99 factorial. So then this gives us 100 times 99 factorial over 99 minus k minus 1 factorial, and then k minus 1 factorial, which is just 100 times 99, choose k minus 1. So now let's go back to our sum using this. So the sum we had was basically we want to compute y equals 100 choose 1 plus, which is really 1 times 100 choose 1, 2 times 100 choose 2, plus 3 times 100 choose 3, plus all the way to 100 times 100 choose, right? Yeah. And so using what we just derived above, we could rewrite this as 100 times 99 choose 0 plus 100 times 99 choose 1. So this equals this equals this, plus 100 times 99 choose 2, plus all the way to 100 times 99 choose 99. And so this is starting to look like what we already know how to sum. So this, we could factor out a common factor of 100. And then we get 99 choose 0 plus 99 choose 1 plus 99 choose 2, all the way to 99 choose 99. And that was what we already knew above, is 2 to the 99. So if we plug that in, we get 100 times 2 to the 99. And then the last step is just to try and factorize this. So 100 equals 2 squared times 5 squared. And so this equals 2 to the 101 times 5 squared. Any questions on this one?
Could you please zoom out so I could get a better?
Yeah, I'll also post these notes. I'll post these notes on Piazza after office hours too, so if anyone wants to go back and check or cross-reference their solution, you can take a look and compare.
Okay, thank you.
Yeah. Any other questions?
Oh, please.
All right, then I'll pass it back to Matthew to go over the other problems. Matthew, are you there? Are you able to go over the algebra questions? Oh, I just got a message from Matthew that he'll be back very soon. Cool. So I guess while he's back, I want to just kind of see what you all thought of those combinatorics problems. Are there any concepts there that you might want to review next week in our lecture more? Out of those questions, after you saw the solutions, which ones kind of did you enjoy the most or find the most interesting?
Um,
I-
well, I personally found, I think it was the one about intersections, with the parallel lines. I found that just a bit challenging. Maybe um if I personally go over it and like look at the notes better, then I'll understand it more. I
Mhm.
but it was also a really interesting question.
Yeah, thanks for the feedback. Yeah, it is interesting. I think that one's hard because you can kind of draw out the smaller cases, but then once you get to larger cases, it's hard to, draw out 12 lines and then make sure you're intersecting all of them and see what happens. Yeah. All right. I think Matthew's back, so we can move on to the algebra questions.
Hello. I want to mention one more thing about combinations, and there's so many different applications of combinations. And having worked with thousands of students over the years, one thing that I notice is there's a little bit more time for the uptake of so many different applications of combinations, but you'll see them everywhere. Now that you've learned some of this stuff, you will be able to, if you look for problems on the internet or contest problems, you're going to see so many different types, and they are important to statistics, dramatically important to an understanding of statistics. So if you reach out and you find some resources and build those skills, you're going to find yourself being able to handle a whole lot more mathematics. So give it some practice over time. But let's take a look at the algebra problems now. Let's see here. We'll go ahead and do number one. And number one can be done in a number of different ways. Those of you who can factor well, you might notice that the right-hand side is 21 times 31. And we didn't really cover factoring. I didn't know how far we would get with different techniques, but I'm just going to go ahead and do this in two different ways. If we want to factor, then we're looking at x plus r times x plus s. And that's going to wind up being x squared plus r plus s, x plus rs. So we're looking for two numbers whose sum is -10 and whose product is -651. So one negative number with a slightly higher magnitude and one positive number. And if we factor 651, we wind up with 3 times 7 times 31. So 31 times 21. Those two numbers, 31 and 21, differ by 10. So we can factor this thing into x minus 31 times x plus 21. And if we just want the larger of the two roots, we take the positive one, and that is 31. Though what we spent more time on in class was completing the square. So let's talk about that. If we're looking at x squared minus 10x, we say, hey, we want half of that 10. We want to say x minus 5 squared, which is going to involve a 25. So if we just take the original equation and we add 25 to both sides, now we can do what we set ourselves up to do and take the square root. And add 5 to 26 to get our answer. Any questions or thoughts about this one? Okay. Let's take a look at problem number 3, hexagonal numbers. And hexagonal numbers get hard to draw after the first few, right? So, if we're trying to do this by drawing, it's going to take a very long time. Here's the third hexagonal number. looks, let me see if I can do this right. And here's the third hexagonal number, but what we found was that it was easier to think in terms of the changes, right? And I like to say this, when you're examining a sequence or a series, focus on the changes, focus on the evolution of the terms. And what we talked about was setting up differences, and that those differences, and I'm even going to put a 0 here. We'll say there is the 0th hexagonal number, which we discussed. And if we look at those differences wind up forming themselves an arithmetic progression. The differences of the differences are constant. And so we can build up the terms. So 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, there we go. So what we're doing is we're adding together the first 20 terms of this sequence, right? We start with 0, we add 1, we get 1. We add 5, we get 6. We add 9, we get 15. So we are summing as k goes from 1 to 20, all the numbers in the form 4k minus 3. And we can do that a couple of different ways. One of those ways is to name the beast. And we've got to get the last term right, right? We're adding 19 4s to 1. And we wind up at 77. And if we want to sum this, we can flip those terms around. And add down the columns. There are 20 pairs of terms that each add up to 78. So S is 20 times 78 over 2. And we get our answer, 780. Another way to do this would be to take, we talked about summation form, and we didn't have time to do a lot of this. It wasn't part of the planned lesson. But for those of you who were already good at making use of this sigma notation, we can make use of the formula for triangular numbers. We can break off the minus 3 that is in every term, and we can factor out the 4. And well, I'll actually go back and show what this looks like, but we get 4 times 20 times 21 over 2 minus 3 times 20. And 20 times 21, well, that's 420 times 2, 840, 840 minus 60 is 780 once again. But I just want to point out where these come from so that you can see how it is that I'm factoring this. If we take each of these terms up here, we can rewrite each one of them as 4 times 1 minus 3 plus 4 times 2 minus 3. It's 4 times 3 minus 3, and so on. All the way up to 4 times 20 minus 3, at which point we have 4 times 1 plus 2 plus 3, all the way up to 20. After some reorganization, minus 3 20 times over. And hopefully seeing this the second time around. I know that, like I said, I didn't prepare to do summation notation during class, but we talked about it a little bit. But now seeing it a second time and seeing, the way it is that we can break a summation into two pieces, this may help you with some problems in the future. Any questions or thoughts about this one? Okay, saw that a lot of people got that one, so good. Okay, Jack and Jill. Now we get to the wordy problem. What is it that we need to first do with the wordy problems?
Write down what we know.
Yeah, and write down what we know. Write it down in a way that we understand how to work with. So, I call this just turning the words into math. So let's see. They run up a 5-kilometer hill and then return to the starting point by the same route. I'm going to draw a path that's a hill. Say that's 5 kilometers. Jack has a 10-minute head start and runs at a rate of 15 kilometers per hour uphill and 20 kilometers per hour downhill. Okay, Jill runs 16 kilometers per hour uphill and 22 kilometers per hour downhill. How far from the top of the hill are they when they pass each other, going in opposite directions? Okay. So I'm going to think this through. So Jack starts running before Jill, and he reaches the turnaround point, and then he starts back. Meanwhile, Jill starts running uphill, and she meets Jack somewhere in there. I don't know where that is yet, but you know what? One thing that we notice is together, they've run the whole course, right? Okay, together they've run the entire 10 kilometers. So total distance 10 kilometers. Well, that means that Jack ran the entire 5 kilometers uphill, and he did so at a rate of 15 kilometers per hour. So how long did it take Jack to run up the hill?
20 minutes.
20 minutes, okay. We can convert that to 20 minutes. Okay, so 20 minutes in, Jack is at the top of the hill. So I'm gonna, if you can compute something nicely, you can kind of reset the problem. That's what I choose to do here. I'm gonna say, okay, 20 minutes has passed. In the meantime, Jill runs 16 kilometers per hour uphill. So she's run, let's see, a third of an hour, 16 kilometers per hour. She is already at this point right here, which is 16 over 3. That's when Jack is at the top of the hill. Jill is there. And so essentially, we're going to see the two of them converge in the middle of the remainder of the track. So really, we're talking about a track that is oh, wait a minute. Oh, no. She started 10 minutes late. So she was only running for 10 minutes. Pardon. Oops. Redraw the hill. She's only been running for 10 minutes. So 1/6 of an hour. 16 divided by 6 is 8/3. My apologies. 8/3. So the track in between them is 5 minus 8/3, which is 7/3 of a kilometer long. And now we have Jack running downhill at a rate of 20 kilometers per hour, and Jill running uphill at her uphill rate of 16 kilometers per hour. So maybe the easiest way to work this problem is to say they are approaching each other at a total rate of 36 kilometers per hour. So rate times time equals distance. And if we solve for t, we're going to get some number of hours after the kilometers cancel out, but we get 7 over 108 hours. Then we're going to multiply that by, see, how far are they from the top of the hill when they pass each other? Okay. How far are they from the top of the hill? So we figured out how long after Jack is at the top of the hill now. And I wasn't even sure what I was going to do with this problem, right? Like, yeah, I just started working this year, but this seemed like a good way to think about it. What we know now is that Jack ran downhill at 20 kilometers per hour for this amount of time. So rate, once again, Jack coming down from the hill comes down at a rate of 20 kilometers per hour and does so for 7 108ths of an hour. And if we cancel some numbers here, we get 35 over 27 kilometers. And was that the right answer? Did I do this right? I did not at all memorize these answers. There we go. Yeah, 35 over 27. Good. Any questions or thoughts about this one? What helped here the most for this solution?
I think it was being able to manipulate the rate times time equals distance formula to suit our situation.
Maybe, but you all seemed very, pretty comfortable with rate times time equals distance. But that's fine. Personally, I think that the drawing helps a lot. Draw. A lot of times when we turn words into math, we just think equations, but your drawings and your models, I think these are what simplify your work the most. You make a good drawing or a model, you can answer a whole lot of different problems pretty easily. Reading this just now, I wasn't even sure what the question was. I'd forgotten what the actual problem, question at the end of the problem was, but it made sense to me to go ahead and figure out, where Jack and Jill were relative to each other at the end when Jack had finished climbing the hill, because then we have like definite points, whereas at the beginning, Jill's not even running yet, right? But yeah, good drawing or model allows you to answer a lot of possible questions once you've got the information out there. Okay, let's take a look at number 7. And we have an optimization problem. And I think we only did one of these in class, but I wanted to go ahead and challenge you all with this again. These seem, a little bit tougher than just doing quadratics at first, than just working with quadratics. But as we talked about, it is completing the square, not knowing the quadratic formula, that does the most for you. And what we saw was when we did that, we could focus on the square part and know that that's how we minimize things. So let's take a look. I'm just going to separate out the 2. I'm going to write this as 4x squared plus 3x, and I'm going to kind of just write this 2 out on the side for now. And complete the square with the stuff that has x in it. So what we need to do is cut 3/4 in half. That gives us 3/8. So we're going to square 3/8 and add that in there. (3/8) squared is 9/64, but we have to subtract it back out, right? We can't just add something into the function that's not there. So what we're going to have here is 4 times this stuff, which is x plus 3/8 squared. But then we're going to have also 4 minus 9/64. And then, of course, that plus 2 that we've been carrying down at the end. And finally, we can write this in a way that allows us to optimize, or in this case, minimize. Let's see, minus 9/16 plus 2, it's going to be plus 23/16. I think, check my work. So here we are. What is the smallest possible value? And what we discussed was the square of any real number is at least 0. So we might build things up this way. I call this building the function, or building the inequality. We know that that's true. We can multiply both parts of this inequality by 4. So that's true. And now we add 23/16 to both sides. And finally, that's the same thing as saying that 4x squared plus 3x plus 2 is at least as large as 23/16. And we know that we can achieve 0 by letting x equal minus 3/8 right there. If we plug in x equals negative 3/8, we do get exactly 23/16, showing that we can achieve the minimum. And by the way, not that we asked this here, but what would this look like if we graphed it?
It would be a curve.
Okay, tell me more.
And then the lowest point would be 23/16, like the turning point, as I would, I'm not sure the word.
That's right, we call that the vertex. We mentioned that a couple of days ago, but for very briefly, but for those of you who haven't had parabolas yet, and that's the curve that we're going to make is a parabola. And somebody tell me, where is that vertex located?
Um, 1/7/16. So that's the y value that we'll have, and so it should be on. It should be 0, 1, 7/16.
Not 0. How do we?
No, it will be minus 3/8.
Minus 3.
The x part.
Good, good. So right about there, maybe. And then it's kind of nice. We can plug in 0 for x and get 2 pretty easily as the output, right? So that kind of helps us, quickly establish. Oops. We have a line of symmetry coming down, and then we can just probably graph a few points to get the shape of the curve good, but there we go, something like that. My art is not very good. But yeah, that's how we find the vertex of a parabola. That's how we find the minimum or the maximum of a quadratic function. By the way, we didn't do an example of this, but when will a quadratic function have a maximum and not a minimum?
When the coefficient of x squared is less than 0.
Right. If we had something that had a negative sign out front right there, then we would be, getting 0 and negative numbers after we squared. And so that would give us a maximum instead of a minimum. Okay. What problem was that? Number 7. So number 9. Okay. One of my favorite problem solving questions is two of them. What's interesting and what's ugly? You've heard me say that before. What's interesting and what's ugly? What's ugly?
Fractions and square roots.
Fractions and square roots. Very reasonable answer. What's interesting?
The repeats of the square root.
Yeah. Yeah, that ugly square root is in more than one place. So in our dismay, we look for a way to use what's interesting to handle what's ugly. What do we do?
We can put the 12 over 7 minus that same root for x back into it. No, we could multiply by the conjugate of 7 minus root x.
Perhaps.
And the non
Perhaps. But I just want to get rid of what's ugly. I just want to...
Could we raise both sides by 4?
Ooh, 7 minus the 4th root of x taken to the 4th power, that's going to be ugly to expand. I don't want to expand our ugliness. I don't want that radical to be there at all.
We could substitute it with another variable, let's say a or b.
I like that idea. Let a equal the 4th root of x. We take that ugly thing and we rename it. We say you are king variable now. And the king variable will conquer. This looks much nicer already, right? We still have the fraction, we still have a variable and a denominator, but that's much easier to deal with. What can we do now?
We could cross multiply.
You could call it cross multiplication or just multiplying both sides by 7 minus a. And now what we have is a pretty standard quadratic. And if you wanted, you could complete the square, but this one is not too hard to factor. We're just looking for factors, looking for 3 plus 4 is 7, 3 times 4 is 12. But now what we need to do is go back and get x. So we say, okay, if a is 3, then 3 is the 4th root of x. So what is x?
81.
Yeah, 3 to the 4th power. And we also have 4 to the 4th power, and we want the sum of the solutions to the equation. So what's 4 to the 4th?
256.
And that's our answer. Any questions or thoughts about this one? Yeah, now that I know that a lot of you have had a little bit of algebra, and now you're beginning to see, more and more algebra. Anytime you stumble across something that is ugly, there is the potential that you can just rename it, right? Just like we did with geometric series when we said, hey, let's name the beast. And sometimes you can even rename entire expressions. But I find that with radicals in particular, I do a lot of renaming, a lot of substitution. Okay, let's look at number 11. So I'm going to say this. A few of you got problem number 11. And this was one where we didn't quite, we didn't look at a problem like this during class, but I figured that we had done enough that some of you would find a way through this. Those of you who did found the roots, took the positive root of x squared minus x minus 1, and just did the computations and figured out which numbers needed to be fit in. So we're going to talk about this in a different way, but let's first solve the quadratic. And you can do this in a number. If you chose to do this with the quadratic formula, I don't blame you. And we get 1 plus or minus root 5 over 2. And by the way, this is kind of a famous quadratic. What is the positive root here? Do any of you recognize that number?
1 plus root 5 over 2.
Have any of you heard of the golden ratio?
Yeah.
Yeah.
I figured some of you had. It's kind of famous. It shows up in art and architecture. And well, this is it right here. It comes from this quadratic. And we can do a lot of instructive things with it. But in particular, what we want is r squared, where we know that r squared equals r plus 1. We want r to the 8th power, but you know what r to the 8th power is? It's r squared, r squared to the 4th power. So what we're looking for is r plus 1 to the 4th power. And this is not the only direction we can go with this, right? Wendy, have you covered binomial expansion?
I haven't.
You have not? Okay. There are different ways that we can go with this. I call this power reduction. Anytime you have a variable and it's equal to stuff that makes, that is made up of smaller powers of the variable, r squared equals r plus 1, you can use that equation to gradually reduce powers. But you know what, let's do this. Let's call this r squared times r squared times r squared times r squared, which is equal to r plus 1 times r plus 1 times r plus 1 times r plus 1. And that gives us, I'll multiply these 2 at a time. But the r squared we can replace. R squared is r plus 1. So what is each of those factors equal to?
Is it
3r
plus 2?
3r plus
2 squared.
Yeah, we have 3r plus 2 squared. And if we multiply that out, we get 9r squared plus 12r plus 4. And now we can replace r squared again. And we get 21r plus 13. So our answer is 21 comma 13. Any questions or thoughts about this one? So now that we've done this, this is a perfectly reasonable solution, but I want to go through another method for doing this. Again, it's going to be power reduction, but it's power reduction that shows something very special happening. And I'm going to go ahead and rename the golden ratio. I'm going to start calling this phi. Say phi squared equals phi plus 1. And let's say that we want to compute phi cubed. Well, that's phi squared times another power of phi, but we know what phi squared is. It's phi plus 1. And we can replace phi squared again with phi plus 1. And we get 2 phi plus 1. Okay, how about phi to the 4th power? Well, we can just go about multiplying one new power of phi at a time into this. We know that phi cubed is 2 phi plus 1. We just found that out. And that's equal to 2 phi squared plus phi. But we can replace 2 phi squared with 2 times phi plus 1. And finally, we have 3 phi plus 2. Okay, so what we can see is that at each point in time, when we add one more power to phi, that we can always then, use the previous power, that previous form where we have some integer times phi plus an integer. We can multiply that into a new power of phi and then reduce any quadratic term, any quadratic term in phi down to a linear term in phi to get the next one. But this is even more special than that. I'm going to write out the first few results and tell me if you notice anything. Phi to the 0 power is 1. Phi to the 1st power is phi. Phi to the 2nd power is phi plus 1. Phi to the 3rd power is 2 phi plus 1. Phi to the 4th power is 3 phi plus 2. Phi to the 5th power is 5 phi plus 3. Does anybody notice a pattern?
The constant that you're adding increases by 1.
Not necessarily by 1. That happens a couple of times.
I think the
Fibonacci sequence.
Yeah, we have the Fibonacci sequence. Yeah, twice. We have the Fibonacci numbers multiplied by phi, and then the constants are also Fibonacci numbers. Well, technically phi is a constant too, but you know what I mean. That extra integer that's added in there, that's also a Fibonacci number. Yeah, and it turns out that phi to the n power is the nth Fibonacci number times phi plus the n minus 1st Fibonacci number. And that's a wonderful result. And we can see how that's happening too, right? We can see how that's happening because when we get to this point right here where we're multiplying the previous term times phi, and then we are separating out that Fibonacci number, multiplying it by both phi and 1. So that Fibonacci number moves, the Fibonacci number that had previously been multiplied by phi now moves to being the integer part. And the next, the new phi is that one plus the coefficient from this number right here. So we have 2 plus 1 equals 3. And the next time around, we'll have 3 plus 2 equals 5. You like that? Any questions or thoughts about this one? Okay. So we've covered all the test problems. Does anyone have a question about anything on the test? Well then, I guess we'll call it a day. Thanks for joining us for office hours, and I'll see you all on Monday.
Thank you for today's lesson.
Thank you, Mr. Crawford.
Mr. Crawford. Thank you, Miss Wendy.
Thank
Thanks
you.
for coming.
Thank you, Miss Wendy.
Enjoy your weekend.
Have a good weekend, everybody.